Picture this. You're standing at the edge of a black hole and your friend is watching you from a safe distance. To them, you appear to be moving in slow motion, like a movie playing at half speed. Your words stretch out into an incomprehensible drawl. Your gestures become sluggish and dreamlike. But from your perspective, everything feels completely normal. Time itself is moving at different speeds for both of you. This isn't science fiction. This is the mind-bending reality of how gravity warps the very fabric of time itself. Today, we're diving deep into one of the most revolutionary discoveries in physics. The phenomenon that proves time isn't the constant, unchanging force we thought it was. We're exploring time dilation, and by the end of this journey, you'll understand why a clock on the top floor of a skyscraper literally runs faster than one in the basement, why GPS satellites need constant time corrections to work properly, and why the stronger gravity gets, the slower time moves. Let's begin this journey into the weird world where gravity and time collide. This isn't just theoretical physics locked away in textbooks. Time dilation is happening all around you right now, every single second of every day. The gravity from Earth is making time move slower for you compared to someone floating in space. The difference is tiny, but it's real, it's measurable, and it's affecting your life in ways you never imagined. I'm about to reveal how Einstein discovered this impossible truth, why it completely shattered our understanding of reality, and how modern technology depends on accounting for time dilation to function. We'll explore the experiments that proved time really does slow down in stronger gravity, examine the mathematical relationship that governs this effect, and see how extreme gravitational fields can create time differences so dramatic they seem to break the laws of physics. And trust me, once you understand how gravity manipulates time, you'll never look at the universe the same way again. Every step you take, every floor you climb, every moment you spend closer to Earth's center is subtly altering the speed at which you experience time itself. The story starts with a man who dared to question everything we thought we knew about time and space. In 1907, Albert Einstein was working as a patent clerk in Switzerland when he had what he later called the happiest thought of his life. He imagined a person falling freely in a gravitational field, and he realized something profound. That falling person wouldn't feel gravity at all. They would feel weightless, just like an astronaut floating in space. This simple thought experiment led Einstein to a conclusion that would revolutionize physics forever. Einstein realized that gravity and acceleration are fundamentally the same thing. If you're in a windowless elevator, there's no experiment you can perform to tell whether you're sitting still in Earth's gravity or accelerating upward through space at 9.8 meters per second squared. This became known as the equivalence principle, and it was the key that unlocked one of the universe's deepest secrets. But Einstein didn't stop there. He pushed this idea further and discovered something that still makes physicists' heads spin today. If gravity and acceleration are equivalent, and if acceleration affects time, then gravity must affect time too. This wasn't just a wild guess. Einstein worked out the mathematics, and the equations told him something impossible. Time runs slower in stronger gravitational fields. Think about that for a moment. Einstein was claiming that time itself, the one thing humans had always assumed was constant and unchanging throughout the universe, actually speeds up and slows down depending on how strong gravity is around you. To most people in 1907, this sounded like complete nonsense. Time was time. A second was a second, whether you were on Earth, on the moon, or floating in the depths of space. But Einstein's mathematics were clear. The stronger the gravitational field, the slower time moves relative to weaker gravitational fields. This effect is called gravitational time dilation, and it's one of the most counterintuitive predictions in all of physics. Yet every experiment we've ever done has confirmed Einstein's prediction with stunning accuracy. Here's how it works. Gravity doesn't just pull on matter and energy. It literally warps the fabric of space-time itself. Imagine space-time as a stretched rubber sheet. When you place a massive object like a planet or star on this sheet, it creates a depression. The more massive the object, the deeper the depression. This warping of space-time is what we experience as gravity. But here's the crucial part. Time is woven into this fabric, along with space. When gravity warps space-time, it warps time along with it. The deeper you go into a gravitational well, the more time gets stretched out. What feels like normal time to you feels like slow motion to someone in a weaker gravitational field watching from a distance. This creates one of the most mind-bending consequences in physics. Identical twins could experience dramatically different amounts of time depending on where they spend their lives. If one twin lived their entire life on Earth while the other lived on a massive planet with stronger gravity, the twin in stronger gravity would age more slowly. When they reunited after decades, the twin from the high-gravity planet would be noticeably younger. The mathematics behind this effect are surprisingly elegant. Einstein showed that time dilation follows a precise relationship. The stronger the gravitational field, the more dramatically time slows down. Near a black hole, where gravity reaches its most extreme values, time dilation becomes so severe that a few minutes near the event horizon could equal years or even decades for someone watching from a safe distance. But you don't need black holes to observe time dilation. The effect happens everywhere gravity exists, including right here on Earth. The difference is usually tiny, but it's real and measurable with modern atomic clocks. A clock on the ground floor of a building runs slightly slower than an identical clock on the top floor, because the ground floor is deeper in Earth's gravitational well. This revelation completely changed how we think about time and space. Before Einstein, scientists treated time and space as separate, absolute quantities. Time flowed at the same rate everywhere in the universe, and space was just an empty stage where events played out. Einstein showed us that time and space are intimately connected, forming a unified fabric called space-time that can be stretched, compressed, and warped by matter and energy. The implications go far beyond academic physics. Every GPS satellite orbiting Earth experiences slightly weaker gravity than we do on the surface, which means their onboard clocks run about 38 microseconds faster per day compared to clocks on Earth. That might not sound like much, but GPS requires nanosecond precision to calculate your location accurately. Without correcting for gravitational time dilation, GPS would accumulate errors of several miles per day, making the system completely useless. Modern particle accelerators also have to account for time dilation effects. When particles are accelerated to near light speed, they experience time dilation due to their motion, but they also experience gravitational time dilation as they move through Earth's gravitational field. The combination of these effects has to be precisely calculated to predict how particles will behave during experiments. Even more remarkably, astronomers use gravitational time dilation to study distant cosmic objects. When light from a distant star passes close to a massive object like a galaxy or black hole, the light gets redshifted due to gravitational time dilation. This gravitational redshift tells us about the strength of gravitational fields in distant parts of the universe and helps us understand the structure of spacetime on cosmic scales. The discovery of gravitational time dilation also opened up entirely new areas of physics. It led to our understanding of black holes, where time dilation becomes so extreme that time appears to stop completely at the event horizon. It helped us understand how massive objects like neutron stars can exist, where gravity is so strong that a teaspoon of material would weigh as much as a mountain on Earth. Time dilation even plays a role in cosmology, the study of the universe as a whole. The expansion of the universe creates a kind of cosmic time dilation effect, where distant galaxies appear to be moving in slow motion compared to nearby objects. This effect helps us understand the history and evolution of the cosmos over billions of years. But perhaps the most profound implication of gravitational time dilation is philosophical. It forces us to abandon our intuitive understanding of time as something absolute and universal. Instead, time becomes something personal and relative. Your experience of time depends on where you are and how fast you're moving. There's no universal clock ticking away somewhere in the cosmos. Every observer has their own personal timeline, and these timelines can diverge in dramatic ways depending on the gravitational environments they experience. This leads to some truly mind-bending scenarios. Imagine you're an astronaut on a mission to explore a massive planet with extremely strong gravity. You spend what feels like a few hours on the surface collecting samples and conducting experiments. When you return to your spaceship orbiting safely above the planet, you discover that days or weeks have passed for your crewmates. Your few hours on the surface stretched into a much longer period for observers in weaker gravity. These effects become even more extreme near black holes. The movie Interstellar famously depicted a scene where astronauts visit a planet near a massive black hole. Due to gravitational time dilation, 1 hour on the planet's surface equals 7 years for people farther away from the black hole. While this specific ratio was exaggerated for dramatic effect, the underlying physics is completely accurate. Time really does slow down dramatically in strong gravitational fields. The precision with which we've measured gravitational time dilation is absolutely stunning. Modern atomic clocks are so accurate they can detect the tiny time dilation effects caused by raising the clock just a few centimeters higher in Earth's gravitational field. These measurements confirm Einstein's predictions to more than 15 decimal places, making gravitational time dilation one of the most precisely tested effects in all of physics. Scientists have even used atomic clocks to measure the shape of Earth's gravitational field with incredible precision. By comparing clock rates at different locations and elevations, researchers can map tiny variations in gravity caused by underground geological features, ocean currents, and even changes in groundwater levels. This technique, called relativistic geodesy, opens up new possibilities for studying Earth's interior structure and monitoring environmental changes. The technology behind these ultra-precise measurements is advancing rapidly. Optical atomic clocks now exist that are so sensitive they can detect gravitational time dilation effects over height differences of just a few millimeters. These clocks are helping scientists test Einstein's theory of general relativity with unprecedented precision and search for any deviations that might reveal new physics beyond our current understanding. But gravitational time dilation isn't just about exotic physics experiments and space missions. It's woven into the fundamental structure of reality itself. Every atom in your body, every chemical reaction in your cells, every electrical signal in your brain is experiencing time at a rate determined by your position in Earth's gravitational field. The fact that you're sitting here reading this, rather than floating in the vacuum of space, means you're experiencing time slightly slower than you would in a gravity-free environment. This creates a fascinating paradox. The stronger gravity feels to you, the slower time moves for you relative to the rest of the universe. It's as if gravity trades spatial freedom for temporal freedom. The more tightly gravity holds you in place, the more it slows down your journey through time. This trade-off between space and time is one of the most beautiful and mysterious aspects of Einstein's theory of relativity. Understanding gravitational time dilation also helps us appreciate just how special and fragile our existence is. Earth's gravity is strong enough to hold on to our atmosphere and create the stable conditions necessary for life, but not so strong that time dilation effects make communication with space missions impossible. We exist in a gravitational sweet spot that allows both complex chemistry and reasonable time coordination across our local cosmic neighborhood. As we continue to explore space and search for life on other worlds, gravitational time dilation will become an increasingly important consideration. Colonies on planets with different gravitational strengths will experience time at different rates. Communication delays won't just be due to the speed of light traveling across vast distances. They'll also be due to the fact that different worlds will have different rates of time flow. The study of gravitational time dilation has also led to some of the most successful tests of Einstein's general theory of relativity. Every measurement we've made, from laboratory experiments with atomic clocks to observations of pulsars orbiting massive companions, confirms that gravity really does slow down time exactly as Einstein predicted. These tests have pushed the boundaries of experimental precision and opened up new frontiers in fundamental physics. But the real magic happens when we dive deeper into the mathematics that govern this phenomenon. Einstein's field equations reveal that gravitational time dilation follows an incredibly precise formula. The relationship between gravity and time isn't random or approximate. It's governed by exact mathematical laws that predict precisely how much time will slow down in any given gravitational field. The formula itself is deceptively simple. Time dilation depends on something called the gravitational potential. The deeper you are in a gravitational well, the stronger this potential becomes, and the more dramatically time slows down. It's like being at the bottom of a valley versus standing on a mountaintop. The valley represents stronger gravity and slower time, while the mountaintop represents weaker gravity and faster time. What makes this even more fascinating is that the effect isn't linear. Time doesn't slow down at a steady rate as gravity gets stronger. Instead, the relationship follows what mathematicians call a square root function. This means that as you get closer to extremely massive objects, time dilation effects accelerate dramatically. The difference between being 1,000 miles from a black hole versus 100 miles from a black hole isn't just 10 times greater, it's exponentially more extreme. This mathematical relationship has allowed physicists to make incredibly precise predictions about time dilation effects throughout the universe. We can calculate exactly how much time slows down on the surface of Jupiter compared to Earth. We can predict the time dilation experienced by spacecraft traveling to different planets. We can even estimate the time effects near exotic objects like neutron stars and black holes that we've never directly visited. The precision of these calculations is absolutely mind-blowing. When NASA sends spacecraft to other planets, mission controllers have to account for gravitational time dilation effects to ensure that onboard clocks stay synchronized with Earth-based timing systems. The differences are tiny, but in the world of space navigation, tiny errors compound into massive problems over the months or years it takes to reach distant destinations. Consider what happens during a mission to Mars. The spacecraft experiences continuously changing gravitational fields as it travels from Earth to Mars. Near Earth, it experiences strong gravitational time dilation. As it moves farther into space, it enters weaker gravitational fields where time runs faster. Then, as it approaches Mars, it enters that planet's gravitational influence, which is weaker than Earth's, but still significant enough to affect onboard clocks. Mission planners have to track these constantly changing time dilation effects throughout the entire journey. They use sophisticated computer models that calculate the gravitational influence of the Sun, Earth, Mars, and even Jupiter and other planets as the spacecraft travels through the solar system. The final result is a complex timeline that shows exactly how onboard clocks will drift relative to Earth time throughout the mission. These calculations become even more complex for missions that involve multiple gravitational assists, where spacecraft use the gravity of planets to change their trajectory and speed. Each gravitational encounter creates its own time dilation effects that have to be precisely calculated and accounted for. The mathematical models used for these calculations involve some of the most sophisticated physics and computer science techniques available today. But the mathematics of time dilation reveal something even more profound about the nature of reality itself. Einstein's equations show us that space and time aren't just connected, they're two aspects of the same fundamental thing. When gravity warps space, it automatically warps time along with it. You can't have one without the other. This unity of space and time creates some truly bizarre consequences. Imagine you could somehow grab onto the fabric of space-time and stretch it like taffy. As you stretch the spatial dimensions, you would automatically be stretching the temporal dimension as well. Time would slow down in the regions where you've stretched space-time, while running faster in regions that remain undeformed, Massive objects like stars and planets are essentially doing exactly this. Their gravity grabs onto space-time and creates depressions like bowling balls placed on a stretched rubber sheet. These depressions in space-time automatically create regions where time runs at different speeds. The deeper the depression, the slower time moves in that region. This geometric view of gravity and time dilation helps explain why the effects are so universal and precise. Every massive object in the universe creates its own pattern of space-time curvature, and these patterns combine in mathematically predictable ways. When you're standing on Earth's surface, you're experiencing the combined gravitational effects of Earth, the Sun, the Moon, and every other massive object in the universe, though the nearby objects dominate the effect. The mathematical elegance of gravitational time dilation extends to some truly exotic scenarios. Near rotating black holes, called Kerr black holes, space-time doesn't just curve inward, it actually gets dragged around by the black hole's rotation, creating a phenomenon called frame dragging. This creates even more complex time dilation effects, where time can flow at different rates in different directions around the black hole. Scientists have discovered that some of these rotating black holes could theoretically create closed time-like curves, regions of space-time where you could travel into your own past. While we don't know if such extreme scenarios actually exist in nature, the mathematics of general relativity allows for these possibilities under certain conditions. The study of these exotic solutions to Einstein's equations continues to reveal new insights about the fundamental nature of time and causality. The mathematical framework of time dilation has also led to revolutionary advances in our understanding of the universe's structure and evolution. When astronomers observe distant galaxies, they have to account for multiple types of time dilation effects. The light from these galaxies has traveled through regions of space with different gravitational fields, and each region has left its own signature on the light's properties. By carefully analyzing these signatures, astronomers can map the distribution of matter and energy throughout the universe. They can identify massive galaxy clusters, detect dark matter halos, and even study the large-scale structure of spacetime itself. Gravitational time dilation has become one of our most powerful tools for understanding cosmic architecture on the largest scales imaginable. The mathematics also reveal something profound about the relationship between energy and time. Einstein's famous equation E equals mc squared is actually just one piece of a larger mathematical framework that describes how mass, energy, space, and time are all interconnected. When massive objects create gravitational fields, they're not just bending space, they're creating regions where energy itself behaves differently. This connection between energy and time dilation has practical implications for everything from nuclear reactors to particle accelerators. High-energy processes naturally create their own time dilation effects, and engineers have to account for these effects when designing systems that operate at extreme energy levels. The fusion reactions powering our Sun create enough energy density to produce measurable time dilation effects, though these are incredibly small compared to the time dilation caused by the Sun's massive gravitational field. Modern research in gravitational physics continues to push the boundaries of our mathematical understanding. Scientists are studying scenarios involving multiple black holes, colliding neutron stars, and other extreme gravitational environments that create time dilation effects unlike anything we can experience directly. These studies require some of the most powerful supercomputers in the world to solve Einstein's field equations under such extreme conditions. The mathematical precision of gravitational time dilation predictions has also made it one of the most important testing grounds for new theories of gravity. While Einstein's general relativity has passed every test so far, scientists continue to propose alternative theories that might explain certain cosmic mysteries like dark matter and dark energy. Many of these alternative theories make slightly different predictions about time dilation effects, and increasingly precise measurements could potentially detect these subtle differences. One of the most remarkable aspects of the mathematics is how they connect quantum mechanics with gravity through time dilation effects. In the quantum world, Particles exist in superposition states where they can be in multiple locations simultaneously, but gravitational time dilation creates different rates of time flow at different locations, which affects how quantum superposition states evolve over time. This intersection of quantum mechanics and gravitational time dilation is leading to entirely new fields of research. Scientists are studying how quantum entanglement behaves when entangled particles are placed in different gravitational fields. They're investigating whether quantum computers could be used to detect incredibly subtle gravitational waves through their effects on quantum superposition states. These cutting-edge experiments are pushing the boundaries of both quantum physics and gravitational physics simultaneously. The mathematical beauty of gravitational time dilation extends to its role in some of the most fundamental questions in physics. Why does time flow forward rather than backward? How does the arrow of time emerge from the underlying laws of physics? While we don't have complete answers to these questions, gravitational time dilation provides important clues about the deep connection between gravity, thermodynamics, and the nature of time itself. As our mathematical understanding continues to evolve, we're discovering that gravitational time dilation might be the key to understanding some of the biggest mysteries in modern physics. The relationship between gravity and time could hold the secrets to unifying quantum mechanics with general relativity, explaining the nature of dark energy and understanding what happens inside black holes where time dilation effects become infinite. These mathematical insights are driving the development of increasingly sophisticated experiments designed to test the limits of our understanding. From atomic clocks sensitive enough to detect the gravitational effects of individual mountains, to gravitational wave detectors that can measure space-time distortions smaller than 1,000th the width of a proton, we're entering an era where the mathematical predictions of gravitational time dilation can be tested with unprecedented precision. The mathematics tell us that we're only beginning to scratch the surface of what gravitational time dilation can teach us about the fundamental nature of reality. Every new measurement, every more precise experiment, every more powerful computer simulation reveals new layers of complexity and beauty in the relationship between gravity, space, and time. But the real proof that gravitational time dilation isn't just mathematical theory came from a series of experiments that literally changed our understanding of reality forever. In 1959, two physicists named Robert Pound and Glenn Rebka conducted what would become one of the most important experiments in the history of science. They wanted to test Einstein's prediction that gravity affects time by measuring something called gravitational redshift. Their setup was elegantly simple, yet the implications were staggering. They placed a radioactive source at the bottom of a 22.5-meter tower at Harvard University and a detector at the top. The source emitted gamma rays with a very precise frequency, like a cosmic tuning fork ringing at exactly the right note. According to Einstein's theory, as these gamma rays traveled upward against Earth's gravity, they should lose energy and their frequency should decrease slightly. The effect they were looking for was incredibly tiny. The frequency shift was only about 2.5 parts in 1,000 trillion. That's like trying to detect a change in the length of a football field that's smaller than the width of an atom. Yet their experiment worked. The gamma rays arriving at the top of the tower had exactly the frequency shift that Einstein's equations predicted. This wasn't just confirming a mathematical formula. This was proof that time itself runs at different rates depending on your position in a gravitational field. The gamma rays were like little clocks, and their frequency told the story of how time flowed differently at different heights in Earth's gravity well. The Pound-Rebka experiment opened the floodgates for increasingly sophisticated tests of gravitational time dilation. Scientists realized they had discovered a new window into the fundamental nature of space-time itself. Each new experiment revealed more about how gravity and time interweave in ways that continue to challenge our deepest intuitions about reality. Just 4 years later, physicists took the next logical step. If gamma rays experience gravitational time dilation, then actual clocks should too. In 1963, researchers strapped atomic clocks to airplanes and flew them at different altitudes. Sure enough, the clocks at higher altitudes, where gravity is slightly weaker, ran faster than identical clocks on the ground. The differences were measured in nanoseconds, but they were real and exactly matched Einstein's predictions. These weren't abstract mathematical concepts anymore. These were actual timepieces telling different times based purely on their position in Earth's gravitational field. The airplane experiments led to even more ambitious tests. Scientists loaded atomic clocks onto rockets and shot them into space, then compared their time with identical clocks left on Earth. They placed clocks at the bottom of deep mines and compared them with clocks on mountaintops. Every single experiment confirmed the same mind-bending truth. Gravity literally controls the flow of time. But perhaps the most dramatic demonstration came from an unexpected source. In the 1970s, astronomers discovered objects called pulsars, which are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. These pulsars are among the most precise clocks in the universe, with some keeping time more accurately than the best atomic clocks on Earth. When astronomers studied pulsars in binary systems, where two massive objects orbit each other, they found something extraordinary. The radio pulses from these cosmic clocks showed exactly the gravitational time dilation effects that Einstein had predicted. As the pulsars moved through different regions of their companion's gravitational field during their orbits, their apparent pulse rates changed in precisely the way general relativity demanded. These pulsar observations provided the first direct evidence of gravitational time dilation occurring in the extreme environments around ultra-dense stellar remnants. The gravitational fields around neutron stars are so intense that time dilation effects become dramatically amplified compared to anything we can create or experience on Earth. The precision of these cosmic experiments is absolutely staggering. Some pulsar timing measurements are accurate to better than 1 part in 100 billion billion. That's equivalent to keeping perfect time for the entire age of the universe and being off by less than a second. When natural laboratories this precise confirm Einstein's predictions, you know you're dealing with fundamental truths about how the universe operates. Modern experimental techniques have pushed the boundaries of gravitational time dilation measurements to almost unbelievable levels of precision. Optical atomic clocks now exist that are so sensitive they can detect the tiny gravitational time dilation caused by being just 2 centimeters higher off the ground. These clocks are literally measuring how Earth's gravity affects time over distances shorter than the length of your thumb. Scientists have used these ultra-precise clocks to map Earth's gravitational field in ways that were impossible just decades ago. By measuring tiny differences in clock rates at different locations, researchers can detect underground geological features, monitor changes in groundwater levels, and even track the movement of magma beneath active volcanoes. The National Institute of Standards and Technology has built atomic clocks so accurate that they would lose less than 1 second over the entire 14 billion year age of the universe. When these clocks are moved up or down by just a few centimeters, they immediately detect the corresponding change in gravitational time dilation. The precision is so extraordinary that these clocks can literally measure the curvature of space-time in your living room. These measurements have revealed something profound about the nature of reality. Time isn't just affected by gravity, it's sculpted by it. Every massive object in the universe creates its own unique pattern of time dilation, like a fingerprint made of warped space-time. Earth creates one pattern, the moon creates another, and the sun creates yet another. When you're standing on Earth's surface, you're experiencing the combined time dilation effects of all these gravitational sources simultaneously. The experimental verification of gravitational time dilation has also led to some unexpected technological applications. The Global Positioning System relies on atomic clocks aboard satellites orbiting Earth. These satellites experience weaker gravity than we do on the surface, so their clocks naturally run about 38 microseconds faster per day than identical clocks on the ground. If GPS engineers didn't correct for this gravitational time dilation effect, the system would accumulate positioning errors of several miles per day. Your smartphone's ability to pinpoint your location within a few meters depends entirely on our understanding of how gravity affects time. Every time you use GPS to navigate to a restaurant or find your way home, you're relying on Einstein's century-old insights about the relationship between gravity and time. The corrections required for GPS are actually more complex than just accounting for the satellite's position in Earth's gravitational field. The satellites are also moving at high speeds relative to Earth's surface, which creates additional time dilation effects due to their motion. Mission controllers have to calculate and correct for both gravitational time dilation and velocity-based time dilation to keep the system accurate. This dual correction reveals something beautiful about the interconnected nature of space and time. Both gravity and motion affect time flow, and both effects stem from the same underlying geometric properties of space-time. Einstein's theory of relativity shows us that these aren't separate phenomena. They're different manifestations of the same fundamental reality. Experimental tests of gravitational time dilation have also played crucial roles in confirming other aspects of Einstein's theory. When astronomers detected gravitational waves for the first time in 2015, they were measuring ripples in space-time itself, traveling at the speed of light. These gravitational waves create tiny, rapidly oscillating time dilation effects as they pass through space. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detects gravitational waves by measuring how they stretch and compress space along perpendicular directions. But stretching space automatically means stretching time as well, so LIGO is essentially measuring oscillating time dilation effects caused by cataclysmic events like black hole mergers occurring billions of light-years away. Each gravitational wave detection provides another confirmation that space-time really does behave exactly as Einstein predicted. The waves arrive at Earth carrying information about the time dilation effects present in the extreme gravitational environments where they were generated. By analyzing these signals, scientists can study gravitational time dilation occurring in regions of space where gravity is millions of times stronger than anything we experience on Earth. Laboratory experiments continue to push the boundaries of what's possible in testing gravitational time dilation. Researchers are developing new types of atomic clocks that could be sensitive enough to detect the gravitational effects of individual mountains or large buildings. These ultra-sensitive instruments could revolutionize our ability to study Earth's interior structure and monitor geological processes in real time. Some of the most ambitious experiments involve taking atomic clocks into space aboard the International Space Station. Astronauts have conducted precision timing experiments that measure gravitational time dilation effects in the microgravity environment of low Earth orbit. These space-based measurements provide unique perspectives on how gravity affects time in environments that can't be replicated on Earth's surface. Future missions are being planned that would take atomic clocks even farther from Earth, potentially to the Moon or Mars. These missions would allow scientists to study gravitational time dilation across much larger variations in gravitational field strength than are possible within Earth's immediate vicinity. The data from these experiments could provide new tests of general relativity under conditions that haven't been explored before. The experimental verification of gravitational time dilation has also opened up entirely new fields of research. Scientists are now studying how quantum mechanical systems behave in gravitational fields, leading to the emerging field of quantum gravity research. These experiments probe the intersection between Einstein's classical theory of gravity and the quantum mechanical nature of matter and energy. Some researchers are investigating whether gravitational time dilation might affect the fundamental constants of nature. While these constants appear to be truly constant under normal conditions, the extreme gravitational environments near black holes or neutron stars might reveal subtle variations that could point toward new physics beyond our current understanding. The precision of modern gravitational time dilation measurements has also made them powerful tools for testing alternative theories of gravity. While Einstein's general relativity has passed every experimental test so far, scientists continue to propose modifications that might explain cosmic mysteries like dark matter and dark energy. Many of these alternative theories make slightly different predictions about time dilation effects, and increasingly precise experiments could potentially detect these subtle differences. One of the most exciting frontiers involves using gravitational time dilation to study dark matter directly. Dark matter doesn't emit light, but it does have gravitational effects that should create detectable time dilation signatures. Ultra-precise atomic clocks might eventually be sensitive enough to detect the tiny time dilation effects caused by dark matter halos surrounding galaxies, or even dark matter particles passing through Earth. The experimental study of gravitational time dilation continues to reveal new aspects of how gravity and time interact. Recent experiments have measured how Earth's rotation affects local space-time geometry, creating tiny frame-dragging effects that influence time flow. These measurements require some of the most sophisticated experimental techniques ever developed, but they're providing unprecedented insights into the dynamic nature of space-time. As experimental techniques continue to advance, we're approaching the point where we might be able to detect gravitational time dilation effects from sources beyond our solar system. The gravitational fields of nearby stars, stellar remnants, and even distant galaxies create tiny time dilation signatures that could potentially be measured with future generations of ultra-precise atomic clocks. These experiments represent more than just technical achievements. They're fundamentally changing how we understand the nature of time itself. Every measurement confirms that time isn't the universal, unchanging backdrop that human intuition suggests. Instead, time is a dynamic, malleable aspect of reality that responds to the presence of mass and energy in precise, mathematically predictable ways. The experimental verification of gravitational time dilation has transformed Einstein's revolutionary insights from abstract theoretical predictions into established scientific facts. We can now measure, manipulate, and apply these effects in ways that have practical benefits for technology and fundamental science alike. The experiments continue to reveal new layers of complexity and beauty in the relationship between gravity, space, and time. But perhaps the most profound impact of these experiments is philosophical. They force us to abandon our common-sense notions about the nature of time and embrace a reality where time itself is relative, flexible, and intimately connected to the structure of space and the distribution of matter and energy throughout the universe. Every experimental confirmation of gravitational time dilation brings us closer to a complete understanding of how the universe operates at its most fundamental level. The precision and elegance of these measurements demonstrate that we're not just studying abstract mathematical concepts. We're uncovering the actual mechanisms that govern the flow of time itself. The experimental journey that began with Pound and Rebka's simple tower experiment has evolved into a sophisticated exploration of spacetime that continues to yield new discoveries and insights. Each new measurement, each more precise experiment, each more sensitive atomic clock brings us deeper into the heart of one of nature's most beautiful and mysterious phenomena. As we continue to push the boundaries of experimental precision, we're discovering that gravitational time dilation isn't just a curiosity of modern physics. It's a fundamental aspect of reality that affects everything from the GPS in your pocket to the evolution of the universe itself. The experiments prove that Einstein's century-old insights about gravity and time continue to reveal new truths about the cosmos we inhabit. These experimental confirmations opened the door to studying gravitational time dilation in the most extreme environments our universe has to offer, and that's where things get truly mind-bending. Picture the most extreme gravitational laboratory nature has ever created, a neutron star where a mass greater than our Sun is compressed into a sphere just 12 miles across. The gravity on the surface of a neutron star is so intense that it creates time dilation effects that make Earth's gravitational influence look like a gentle breeze. On the surface of a neutron star, time runs approximately 30% slower compared to an observer far from any gravitational influence. This means that if you could somehow survive on a neutron star's surface for what feels like 1 hour to you, an observer watching from a safe distance would see more than an hour and 20 minutes pass on their clock. But neutron stars are just the beginning. The real extreme lies with black holes, where gravitational time dilation reaches its ultimate expression. As you approach a black hole's event horizon, time dilation effects become so severe they approach infinity. Time doesn't just slow down near a black hole, it practically stops. Consider what would happen if you watched someone fall into a black hole. As they approach the event horizon, you would see them moving slower and slower, their image becoming redder and dimmer until they appear frozen at the edge of the black hole, suspended in time forever. Yet from the falling person's perspective, they would pass through the event horizon in a finite amount of their own time, experiencing nothing unusual about their personal timeline. This creates one of the most paradoxical situations in physics. The infalling observer crosses the event horizon and continues toward the black hole's center, experiencing a normal flow of time from their own perspective. But to outside observers, that person appears frozen forever at the event horizon, their image slowly fading as the light becomes too redshifted to detect. The mathematics of extreme gravitational time dilation reveal scenarios that challenge our basic understanding of causality and the nature of time itself. Near the event horizon of a black hole, the curvature of space-time becomes so extreme that the normal relationship between cause and effect begins to break down in ways that are difficult for human minds to comprehend. Scientists have calculated that if you fell toward a supermassive black hole, the kind found at the center of galaxies, the time dilation effects would be so gradual that you might not notice them until you're very close to the event horizon. But for smaller, more compact black holes, the time dilation gradient would be so steep that different parts of your body would experience noticeably different rates of time flow. This creates what physicists call tidal effects, but applied to time rather than space. Your feet, being closer to the black hole, would experience stronger time dilation than your head. This temporal stretching would add to the spatial tidal forces that would ultimately tear apart any object falling into a black hole. The study of extreme gravitational time dilation has led to some of the most bizarre predictions in theoretical physics. Near rotating black holes, the dragging of spacetime can create regions where time flows in loops, potentially allowing for closed time-like curves, where cause and effect become circular rather than linear. These extreme scenarios push the boundaries of what Einstein's equations tell us about the nature of time. In some solutions to the field equations, time can flow backward relative to distant observers, or split into multiple streams that reconnect later. While we don't know if such extreme conditions actually exist in nature, the mathematics suggests they're possible under certain circumstances. The extreme time dilation near black holes also creates fascinating implications for information and communication. If you could somehow establish a communication link with someone falling into a black hole, the messages you receive from them would arrive at increasingly longer intervals due to time dilation effects. Eventually, the time between messages would stretch to years, then centuries, then millennia. From the perspective of the falling observer, they would be sending messages at regular intervals right up until they cross the event horizon. But due to gravitational time dilation, these messages would be spread out over an infinite amount of time as seen by outside observers. The last message sent just before crossing the event horizon would theoretically never arrive. This creates profound questions about the fate of information that falls into black holes. Does the information get destroyed when it crosses the event horizon? Or does it remain encoded in the increasingly time-dilated signals that never quite reach outside observers? This puzzle, known as the black hole information paradox, remains one of the most important unsolved problems in theoretical physics. The extreme gravitational environments around black holes also create opportunities for what scientists call gravitational time travel. While you can't travel backward in time using gravitational effects alone, you can effectively travel into the future by experiencing strong time dilation. If you spent time near a black hole and then returned to a region of weaker gravity, you would find that much more time had passed for the rest of the universe. This form of time travel is completely consistent with the laws of physics as we understand them. It's not science fiction, it's a direct consequence of how gravity affects the flow of time. The only practical limitation is the enormous technological challenge of getting close enough to a black hole to experience significant time dilation while still being able to escape and return to tell the tale. Some theoretical scenarios involve using the extreme time dilation near black holes for practical purposes. A civilization with sufficiently advanced technology might establish research stations near black holes where scientists could conduct experiments that require enormous amounts of time. Due to time dilation, these experiments could run for what seems like millennia from the researcher's perspective, while only years pass for the civilization that sent them. The extreme gravitational fields near black holes also create opportunities for testing the fundamental limits of Einstein's theory. As gravitational fields approach their maximum possible strength, quantum mechanical effects begin to compete with gravitational effects in ways that might reveal new physics beyond our current understanding. Near the center of a black hole, where Einstein's equations predict the formation of a singularity with infinite gravitational field strength, quantum effects must become important. The result might be a quantum bounce that prevents the formation of true singularities or exotic states of matter that exist under conditions of extreme space-time curvature. These extreme scenarios are driving the development of quantum theories of gravity that attempt to unify Einstein's classical description of space-time with the quantum mechanical nature of matter and energy. The extreme time dilation effects near black holes provide a natural laboratory for testing these theories, even if we can't directly access such environments. Astronomers have discovered black holes throughout our galaxy and beyond, each representing a natural laboratory where extreme gravitational time dilation effects are constantly occurring. The supermassive black hole at the center of our own galaxy provides an opportunity to study these effects relatively close to home, astronomically speaking. Recent observations of stars orbiting close to this central black hole have revealed orbital velocities approaching significant fractions of the speed of light. These stars experience both gravitational time dilation from the black hole's immense mass and velocity-based time dilation from their rapid motion. The combination creates complex time dilation effects that test our understanding of relativistic physics. The Event Horizon Telescope, which captured the first image of a black hole's shadow, is also providing new insights into extreme gravitational time dilation. The light that forms these images has traveled through regions of intense space-time curvature, carrying information about the time dilation effects present in these extreme environments. Future space missions might allow us to study extreme gravitational time dilation more directly. Proposed missions to explore black holes would use advanced propulsion systems to approach much closer than is currently possible, potentially allowing direct measurement of extreme time dilation effects while maintaining the ability to escape and report back. The study of extreme gravitational time dilation is also revealing connections between gravity, thermodynamics, and information theory that weren't apparent in less extreme environments. Black holes appear to have temperature and entropy, properties that seem to contradict their classical description as objects from which nothing can escape. These thermodynamic properties of black holes are intimately connected to the extreme time dilation effects near their event horizons. The apparent temperature of a black hole, called Hawking radiation, arises from quantum effects in the extreme gravitational fields where time dilation approaches infinity. The mathematics describing extreme gravitational time dilation near black holes has also led to insights about the holographic principle, which suggests that all the information contained within a volume of space can be encoded on the boundary of that volume. This principle emerged from studies of black hole thermodynamics and the extreme time dilation effects near event horizons. According to the holographic principle, the extreme time dilation near a black hole's event horizon might be related to the way information is encoded and processed at the boundary between the black hole's interior and the external universe. This connection between time dilation and information processing represents one of the most active areas of research in modern theoretical physics. The extreme scenarios created by black holes and neutron stars are also teaching us about the limits of gravitational time dilation itself. While time dilation can become arbitrarily large as you approach a black hole's event horizon, there appear to be fundamental limits to how extreme these effects can become while still maintaining a meaningful description of physical processes. These limits arise from quantum mechanical effects that become important when gravitational fields reach their maximum possible strength. The uncertainty principle of quantum mechanics places fundamental restrictions on how precisely time and energy can be defined simultaneously, which might prevent time dilation from becoming truly infinite even at event horizons. The study of extreme gravitational time dilation continues to push the boundaries of both theoretical understanding and observational capabilities. Each new discovery about black holes, neutron stars, and other compact objects reveals new aspects of how gravity and time interact under the most extreme conditions nature can create. Modern gravitational wave detectors are opening new windows into these extreme environments by detecting the ripples in space-time created when black holes and neutron stars collide. These cosmic catastrophes create gravitational time dilation effects so extreme that they literally shake the fabric of space-time itself, sending waves that we can detect billions of years later. The gravitational waves carry information about the time dilation effects present during these extreme events, allowing scientists to study gravitational physics under conditions that exceed anything possible in terrestrial laboratories. Each detection provides new data about how space-time behaves when gravitational fields reach their most extreme values. Future gravitational wave detectors will be sensitive enough to study even more extreme scenarios, potentially detecting the gravitational signatures of matter falling into black holes or the collision of objects in the most intense gravitational fields in the universe. These observations will provide unprecedented insights into the behavior of time under the most extreme conditions possible. The exploration of extreme gravitational time dilation represents one of the most exciting frontiers in modern physics. Each new discovery reveals new aspects of how time, space, matter, and energy interact when pushed to their absolute limits. The extreme scenarios challenge our understanding while pointing toward new theories that might unify gravity with the other fundamental forces of nature. As our observational capabilities continue to advance, we're gaining access to natural laboratories where gravitational time dilation reaches levels that would have been purely theoretical just decades ago. These extreme environments are teaching us that the relationship between gravity and time is even more rich and complex than Einstein first imagined. The study of extreme gravitational time dilation also highlights the incredible range of time dilation effects present throughout our universe. From the tiny effects measurable with atomic clocks on Earth to the extreme effects near black holes where time nearly stops, gravitational time dilation spans an enormous range of physical scales and conditions. This vast range reveals something profound about the fundamental nature of time itself. Time isn't just affected by gravity, it's sculpted by it in ways that create a rich tapestry of temporal environments throughout the cosmos. Every massive object in the universe contributes to this cosmic symphony of time dilation effects. From the gentle influence of planets and stars to the extreme distortions created by the most compact objects known to exist. Understanding extreme gravitational time dilation helps us appreciate just how special and unusual our everyday experience of time really is. The steady, predictable flow of time we experience on Earth's surface represents just one point in a vast spectrum of possible temporal experiences that exist throughout the universe. But these extreme effects aren't just cosmic curiosities, they're providing crucial insights into the fundamental laws that govern our universe, and they're opening up possibilities for technologies and discoveries that we're only beginning to imagine. As we've seen, gravitational time dilation isn't confined to exotic cosmic phenomena. It's woven into the fabric of everyday life in ways that most people never realize. Every technology that depends on precise timing, every GPS navigation system, every communication satellite, every atomic clock used in scientific research must account for gravitational time dilation effects to function properly. The global positioning system represents perhaps the most visible example of how gravitational time dilation affects modern technology. GPS satellites orbit at an altitude of about 20,000 kilometers above Earth's surface, where they experience significantly weaker gravity than we do on the ground. This difference in gravitational field strength causes the atomic clocks aboard GPS satellites to run approximately 45 microseconds faster per day compared to identical clocks on Earth's surface. While 45 microseconds might seem trivial, GPS requires nanosecond precision to calculate positions accurately. Light travels about 30 centimeters in 1 nanosecond, so timing errors of just a few microseconds would translate to positioning errors of several kilometers. Without corrections for gravitational time dilation, GPS would be completely useless for navigation within a matter of days. The corrections applied to GPS aren't simple one-time adjustments. Mission controllers must continuously monitor and adjust for gravitational time dilation effects as satellites move through their orbits. The satellites don't follow perfectly circular paths, so their distance from Earth's center varies slightly throughout each orbit. These orbital variations create continuously changing gravitational time dilation effects that must be calculated and corrected in real time. GPS engineers also have to account for the fact that Earth's gravitational field isn't perfectly uniform. Mountains, valleys, and variations in the density of Earth's interior create tiny variations in gravitational field strength that affect time dilation differently at different locations. The most accurate GPS systems incorporate detailed models of these gravitational variations to achieve the highest possible positioning accuracy. Modern smartphones and navigation devices perform millions of these gravitational time dilation calculations every day without users ever realizing it. Every time you check your location on a map app or get turn-by-turn directions to a destination, you're relying on Einstein's insights about how gravity affects time. The convenience of modern navigation technology exists only because we understand and can correct for gravitational time dilation effects. The telecommunications industry also depends heavily on accurate timing that must account for gravitational time dilation. Cell phone towers, internet infrastructure, and satellite communication systems all rely on precise synchronization that would be impossible without correcting for the time dilation effects experienced by satellites and ground-based equipment at different elevations. Financial markets represent another unexpected application of gravitational time dilation corrections. High-frequency trading systems that execute thousands of transactions per second require incredibly precise timing to function properly. The atomic clocks used to timestamp these transactions must account for their exact elevation and gravitational environment to maintain the nanosecond accuracy needed for fair and orderly markets. The precision required for modern financial timing is so extreme that some trading firms have moved their servers to lower floors of buildings to take advantage of the slightly slower time flow closer to Earth's center. While the effect is incredibly small in the world of high-frequency trading where microseconds can mean millions of dollars, even tiny gravitational time dilation effects become economically significant. Power grid synchronization provides another critical application of gravitational time dilation understanding. Electrical power grids must maintain precise frequency synchronization across vast geographic areas to prevent blackouts and equipment damage. The atomic clocks used to coordinate power generation and distribution must account for their elevation and local gravitational environment to maintain the required timing accuracy. Modern internet infrastructure depends on network time protocol servers that provide precise timing information to computers around the world. These timing servers use atomic clocks that must be corrected for gravitational time dilation effects based on their geographic location and elevation. The result is a global network of synchronized time that enables everything from email delivery to online banking to function properly. Scientific research facilities represent some of the most demanding applications of gravitational time dilation corrections. Particle accelerators like the Large Hadron Collider require femtosecond timing precision to coordinate the acceleration and collision of subatomic particles. The timing systems must account for the gravitational time dilation effects experienced by equipment located at different elevations within the facility. Radio astronomy observatories use arrays of telescopes distributed across continents to create virtual telescopes with incredible resolution. These arrays require precise timing synchronization that must account for the different gravitational environments experienced by telescopes at different locations and elevations. The timing precision needed for these observations approaches the fundamental limits of what's possible with current atomic clock technology. Space missions represent perhaps the most complex applications of gravitational time dilation corrections. Spacecraft experience continuously changing gravitational fields as they travel between planets, requiring mission controllers to constantly recalculate time dilation effects. Deep space missions that last for years or decades must maintain timing accuracy despite experiencing gravitational influences from multiple planets and the Sun. The Voyager spacecraft, now traveling in interstellar space, have been correcting for gravitational time dilation effects for more than 4 decades. As these spacecraft move farther from the Sun's gravitational influence, their onboard clocks gradually speed up relative to Earth time. Mission controllers must account for these effects to maintain communication and navigation accuracy across billions of miles of space. Mars missions present particularly complex gravitational time dilation challenges. Spacecraft traveling to Mars experience the gravitational influences of Earth, Mars, and the Sun in constantly changing combinations. The time dilation effects vary continuously throughout the journey, requiring sophisticated computer models to predict and correct for timing variations. The International Space Station provides a unique laboratory for studying gravitational time dilation effects in a controlled environment. Astronauts aboard the station experience slightly weaker gravity than people on Earth's surface, causing their biological clocks and any timepieces they carry to run slightly faster. These effects are small but measurable, providing ongoing confirmation of Einstein's predictions. Future space exploration missions will face even more complex gravitational time dilation challenges. Missions to Jupiter and Saturn will experience the strong gravitational fields of these giant planets, creating time dilation effects that must be precisely calculated to maintain communication and navigation accuracy. Missions to explore the outer solar system will travel through regions where the Sun's gravitational influence becomes negligible, requiring new approaches to timing and navigation. The development of atomic clocks for space applications continues to push the boundaries of timing precision. Next-generation space clocks will be accurate enough to detect gravitational time dilation effects from individual asteroids and comets, opening up new possibilities for studying the distribution of mass throughout the solar system. Modern geology and geophysics increasingly rely on gravitational time dilation measurements to study Earth's interior structure. By comparing the rates of ultra-precise atomic clocks at different locations, scientists can map variations in Earth's gravitational field that reveal information about underground geological features, groundwater movement, and even tectonic activity. These geodetic applications of gravitational time dilation represent a completely new approach to studying our planet. Instead of drilling deep holes or using seismic waves to probe Earth's interior, Scientists can now use the subtle variations in time flow caused by gravitational field variations to create detailed maps of subsurface structure. Climate scientists are beginning to use gravitational time dilation measurements to study changes in Earth's mass distribution caused by melting ice sheets, changing ocean currents, and atmospheric circulation patterns. These measurements provide a new tool for monitoring global climate change with unprecedented precision and spatial resolution. The applications of gravitational time dilation continue to expand as atomic clock technology becomes more precise and portable. Researchers are developing portable atomic clocks that could be used for real-time geological surveying, earthquake monitoring, and even archaeological investigations of buried structures. Modern technology has become so dependent on accurate timing that gravitational time dilation corrections are now built into the fundamental infrastructure of our connected world. From the GPS in your car to the internet connection in your home, from the power grid that provides electricity to the financial systems that process payments, gravitational time dilation affects nearly every aspect of modern technological society. The remarkable thing is that most people remain completely unaware of these effects. The corrections happen automatically, built into the software and hardware that make modern technology possible. Einstein's revolutionary insights about gravity and time have become so thoroughly integrated into our technological infrastructure that we take them for granted. This hidden influence of gravitational time dilation reveals something profound about the relationship between fundamental physics and everyday life. The most abstract and counterintuitive discoveries about the nature of reality often end up having the most practical and widespread applications. What began as Einstein's thought experiment about falling elevators has become essential knowledge for engineers and scientists working on everything from smartphone navigation to space exploration. The continuing development of more precise atomic clocks and timing systems promises to reveal new applications of gravitational time dilation that we haven't yet imagined. As our ability to measure time with ever greater precision improves, we're discovering that gravitational effects influence more and more aspects of our technological world. The study of gravitational time dilation applications also highlights the incredible precision required for modern technology to function properly. Effects that seem negligibly small from a human perspective become critically important when multiplied across millions of devices and billions of calculations. The universe operates with mathematical precision that demands equally precise technological responses. Understanding these applications helps us appreciate the deep connections between fundamental physics and the technological civilization we've created. Every GPS satellite, every atomic clock, every precisely timed system represents a practical application of our understanding about how gravity shapes the flow of time itself. As we continue to push the boundaries of timing precision and develop new technologies that depend on accurate time measurement, gravitational time dilation will become even more important to our technological infrastructure. The effects that Einstein first predicted over a century ago continue to find new applications in ways that even he probably never imagined. The practical applications of gravitational time dilation also demonstrate how scientific discoveries that initially seem purely theoretical often end up having enormous practical value. What appeared to be an abstract consequence of Einstein's geometric theory of gravity has become essential knowledge for anyone working with precision timing systems or space-based technology. This progression from theoretical insight to practical application represents one of the most beautiful aspects of scientific discovery. The universe reveals its secrets through mathematical equations and thought experiments, but those same secrets often hold the keys to technologies that transform human civilization in profound and lasting ways. The future of gravitational time dilation research promises to unlock secrets about reality that we can barely imagine today. Scientists are developing experimental techniques so sensitive they could detect time dilation effects from objects as small as mountains or as subtle as underground water reservoirs. These advances are opening entirely new frontiers in physics, geology, and our fundamental understanding of how the universe operates. One of the most exciting developments involves quantum sensors that exploit the strange properties of quantum mechanics to measure gravitational time dilation with unprecedented precision. These devices use clouds of ultra-cold atoms trapped by laser light, creating quantum systems so sensitive they can detect gravitational changes equivalent to moving just millimeters closer to or farther from Earth's center. These quantum gravimeters represent a revolutionary leap beyond traditional atomic clocks. While atomic clocks measure time dilation by comparing the frequencies of different atoms, quantum gravimeters directly measure the gravitational field itself by observing how quantum states evolve in response to gravitational forces. The result is sensitivity levels that seemed impossible just decades ago. Scientists are using these quantum sensors to map Earth's gravitational field in extraordinary detail. They can detect underground rivers changing course, magma chambers shifting beneath volcanoes, and even the subtle gravitational effects of buildings and large vehicles passing nearby. This level of sensitivity transforms gravitational time dilation from an abstract physics concept into a practical tool for studying our planet's hidden structure. The implications extend far beyond Earth-based applications. Space agencies are developing plans to deploy quantum gravimeters throughout the solar system, creating a network of gravitational sensors that could map the internal structure of planets and moons with incredible precision. These missions could reveal hidden oceans beneath icy surfaces, detect subsurface geological activity on Mars, and even study the internal structure of asteroids and comets. Future gravitational time dilation research is also pushing toward the quantum realm in ways that could revolutionize our understanding of gravity itself. Scientists are designing experiments to test whether gravitational time dilation affects quantum mechanical processes, potentially revealing new connections between Einstein's classical theory of gravity and the quantum nature of matter and energy. These quantum gravity experiments involve creating quantum superposition states where particles exist in multiple gravitational environments simultaneously. By measuring how these superposition states evolve over time, researchers hope to detect quantum effects in gravitational fields that could point toward a unified theory combining general relativity with quantum mechanics. The precision required for these experiments demands technological capabilities that push the absolute limits of what's currently possible. Scientists are developing atomic clocks accurate to 1 part in 10 to the 18th power, equivalent to losing less than 1 second over the entire age of the universe. These ultra-precise instruments could detect gravitational time dilation effects from sources we haven't even imagined yet. One particularly ambitious project involves placing atomic clocks in orbit around the Sun at different distances, creating a solar system-scale laboratory for studying gravitational time dilation. These space-based clocks would experience dramatically different gravitational environments, allowing scientists to test Einstein's predictions across gravitational field strengths impossible to achieve on Earth. The data from such experiments could reveal whether our understanding of gravitational time dilation remains accurate under extreme conditions, or whether modifications to Einstein's theory become necessary when dealing with very strong or very weak gravitational fields. These tests could uncover new physics that explains cosmic mysteries like dark matter and dark energy. Advanced computer simulations are also playing an increasingly important role in gravitational time dilation research. Supercomputers can now model the complex interactions between multiple massive objects, predicting time dilation effects in scenarios involving colliding black holes, merging neutron stars, and other extreme cosmic events that we can't study directly. These simulations are revealing that gravitational time dilation can create incredibly complex patterns when multiple strong gravitational sources interact. Near binary black hole systems, for example, time dilation effects can vary dramatically over short distances and timescales, creating regions where time flows in completely different ways, just meters apart. The computational challenges involved in these simulations require some of the most powerful computers in the world. Calculating gravitational time dilation effects accurately demands solving Einstein's field equations under conditions where the mathematics become extraordinarily complex. Each simulation can require millions of hours of computer time and generate terabytes of data about space-time geometry. Future research directions include studying gravitational time dilation in the early universe, when the cosmos was much denser and gravitational fields were far stronger than anything we observe today. Computer models suggest that time dilation effects during the first moments after the Big Bang could have created regions where time flowed at drastically different rates, potentially affecting how matter and energy evolved during cosmic inflation. Scientists are also investigating whether gravitational time dilation might provide clues about the nature of dark energy, the mysterious force causing the universe's expansion to accelerate. Some theories propose that dark energy creates its own time dilation effects that could be detected with sufficiently sensitive measurements. The search for gravitational waves has opened another frontier in time dilation research. When gravitational waves pass through space, they create oscillating time dilation effects that ripple through the fabric of space-time itself. Future gravitational wave detectors will be sensitive enough to study these temporal oscillations in detail, providing new insights into how time responds to dynamic gravitational fields. These next-generation detectors will be capable of detecting gravitational waves from sources throughout the observable universe, each carrying information about the time dilation effects present in the extreme gravitational environments where they originated. The data could reveal how time behaves near the event horizons of black holes, inside neutron stars, and during other cosmic catastrophes. Laboratory experiments are also becoming increasingly sophisticated. Scientists are developing techniques to create artificial gravitational fields using ultra-intense laser pulses, magnetic fields, and rapidly rotating systems. While these artificial fields are much weaker than natural gravitational sources, they allow controlled studies of how time dilation affects scale with field strength. Some of the most intriguing future possibilities involve using gravitational time dilation for practical applications that seem like science fiction today. Researchers are exploring whether controlled time dilation effects could be used for data storage, quantum computing, or even communication systems that take advantage of different rates of time flow. The concept of chronometry, precise measurement of time differences caused by gravitational effects, is emerging as a new scientific discipline. Chronometric techniques could revolutionize fields ranging from archaeology to environmental science by providing new ways to study processes that occur over long time scales. Future space missions will rely increasingly on understanding and predicting gravitational time dilation effects. As spacecraft travel to more distant destinations and spend longer periods in space, the cumulative effects of time dilation become more significant. Mission planners are developing sophisticated models that account for every gravitational influence throughout multi-year journeys to the outer solar system. The possibility of human missions to Mars and beyond raises fascinating questions about how gravitational time dilation will affect space travelers. Astronauts spending months or years in the different gravitational environments of other worlds will experience time at different rates compared to people on Earth. While the effects will be small, they represent the first steps toward a future where humans routinely experience different flows of time. Advanced propulsion systems under development could eventually allow spacecraft to reach regions of space where gravitational time dilation effects become more significant. Missions to study black holes, neutron stars, and other extreme objects could provide direct measurements of time dilation under conditions impossible to replicate in terrestrial laboratories. The study of gravitational time dilation is also driving the development of new mathematical tools and computational techniques. The equations describing time dilation in complex gravitational environments often can't be solved analytically, requiring numerical methods that push the boundaries of computational physics. Machine learning and artificial intelligence are beginning to play important roles in analyzing gravitational time dilation data. These systems can identify subtle patterns in timing measurements that might reveal new gravitational sources or unexpected variations in time dilation effects. AI algorithms are particularly useful for processing the enormous datasets generated by networks of atomic clocks and gravitational sensors. Future research will likely reveal connections between gravitational time dilation and other fundamental physics phenomena that we haven't yet discovered. The precision of modern measurements is approaching levels where quantum effects, relativistic corrections, and other subtle influences become detectable, potentially opening new windows into the deeper structure of reality. The technological applications of gravitational time dilation research continue to expand in unexpected directions. Ultra-precise timing systems based on gravitational effects could enable new forms of secure communication, navigation systems that work in environments where GPS is unavailable, and scientific instruments capable of detecting incredibly subtle changes in Earth's environment. Medical applications represent an emerging frontier where gravitational time dilation might play a surprising role. Some researchers are investigating whether the tiny time dilation effects experienced by different parts of the human body could influence biological processes in measurable ways. While such effects would be extraordinarily small, the precision of modern measurement techniques is approaching levels where even these subtle influences might become detectable. The philosophical implications of future gravitational time dilation research are equally profound. As our understanding of how gravity shapes time becomes more complete, we're forced to confront fundamental questions about the nature of existence, consciousness, and our place in a universe where time itself is relative and malleable. Future discoveries in gravitational time dilation research could reshape our understanding of causality, free will, and the relationship between mind and matter. If time really is as flexible and relative as Einstein's equations suggest, what does that mean for our concepts of past, present, and future? How do we understand consciousness and memory in a universe where different observers can legitimately disagree about the order of events? The ongoing research into gravitational time dilation represents more than just an academic exercise or technological development. It's a fundamental exploration of the nature of reality itself, probing the deepest connections between matter, energy, space, and time. Every new measurement, every more precise experiment, every more sophisticated theory brings us closer to understanding the true nature of the universe we inhabit. As we stand on the threshold of even more remarkable discoveries, gravitational time dilation continues to challenge our assumptions and expand our understanding of what's possible. The phenomenon that Einstein first predicted as a consequence of his geometric theory of gravity has evolved into one of the most active and exciting areas of modern physics research. The future promises discoveries that will make today's understanding of gravitational time dilation seem primitive by comparison. We're entering an era where the manipulation and control of time dilation effects might become as routine as the manipulation of electromagnetic fields is today. The implications for technology, science, and human civilization are staggering to contemplate. But perhaps the most remarkable aspect of gravitational time dilation research is how it continues to reveal new layers of beauty and complexity in the relationship between gravity and time. Each new discovery demonstrates that reality is far stranger, more elegant, and more interconnected than our everyday experience suggests. The journey that began with Einstein's simple thought about a falling elevator has evolved into a comprehensive exploration of space-time that touches every aspect of modern physics and technology. As we continue to push the boundaries of what's possible in measuring and understanding time dilation effects, we're not just advancing scientific knowledge. We're uncovering the fundamental principles that govern the universe itself. The story of gravitational time dilation is far from over. In fact, we may be just beginning to understand the full implications of how gravity shapes the flow of time. The discoveries awaiting us in the coming decades could revolutionize not just physics and technology, but our entire understanding of what it means to exist in a universe where time itself bends to the will of gravity. From the quantum realm to the cosmic scale, From everyday technology to the most extreme environments in the universe, gravitational time dilation continues to reveal new secrets about the nature of reality. The phenomenon that once seemed like an impossible prediction from abstract mathematics has become one of the most practical and important aspects of modern science and technology. As we look toward the future, one thing becomes clear: our journey into understanding how gravity affects time has only just begun. The most remarkable discoveries about the relationship between gravity and time may still be waiting for us, hidden in the equations of physics and the structure of space-time itself. Every tick of every clock, every measurement of every atomic transition, every observation of every cosmic event contributes to our growing understanding of how gravity sculpts the flow of time throughout the universe. We're living through a golden age of discovery where the most fundamental aspects of reality are yielding their secrets to human curiosity and ingenuity. The universe has been running this incredible experiment in gravitational time dilation for nearly 14 billion years, creating a cosmic laboratory where every massive object contributes to a symphony of temporal effects that span scales from the quantum to the cosmic. We're finally developing the tools and understanding necessary to read the score of this cosmic symphony and appreciate the elegant mathematical relationships that govern how gravity and time dance together throughout the cosmos. The implications of gravitational time dilation extend far beyond the realm of theoretical physics into territories that challenge our most basic assumptions about existence itself. When we truly grasp that time flows differently depending on where you are in the universe, we begin to realize that our everyday experience represents just one tiny slice of a much larger temporal reality. Consider the profound philosophical questions this raises about the nature of simultaneity. Two events that appear to happen at exactly the same time from one observer's perspective might occur at completely different moments when viewed from another gravitational environment. There is no universal now that applies throughout the cosmos. Instead, each observer carries their own personal timeline that can diverge dramatically from others depending on their gravitational circumstances. This revelation forces us to reconsider fundamental concepts about cause and effect. If time flows at different rates in different gravitational fields, then the sequence of events becomes observer-dependent in ways that challenge our intuitive understanding of how the universe operates. What seems like a clear chain of cause and effect to one observer might appear scrambled or even reversed to another observer in a different gravitational environment. The psychological impact of understanding gravitational time dilation can be overwhelming. We are forced to abandon the comforting notion that time is a reliable, universal constant that provides a stable framework for understanding reality. Instead, time becomes something personal and relative, as dependent on your location and circumstances as your view of the landscape around you. This relativity of time also raises profound questions about the nature of aging and mortality. While we all age at the same rate relative to our own experience, observers in different gravitational environments would measure our aging at different rates. A person living their entire life in a stronger gravitational field would appear to age more slowly when observed from a weaker gravitational environment, even though they would experience their own aging as completely normal. The implications extend to every aspect of human experience that depends on the measurement or perception of time. Music, which depends on precise timing relationships between notes, would sound different to observers in different gravitational environments. The rhythm and tempo that seem natural to you would appear distorted to someone experiencing time at a different rate due to gravitational effects. Language itself becomes complicated when we consider gravitational time dilation. The meaning of words like now, before, and after depends on the gravitational context of the speaker and listener. Communication between observers in dramatically different gravitational environments would require careful consideration of how time dilation affects the transmission and reception of messages. Even more fundamentally, the concept of personal identity becomes complex when we consider that different parts of your body experience slightly different gravitational time dilation effects. Your feet, being closer to Earth's center, experience marginally stronger gravity than your head, causing time to flow at slightly different rates throughout your body. While these effects are incredibly small under normal circumstances, they raise philosophical questions about what it means to exist as a unified being in a universe where time itself is not uniform. The discovery of gravitational time dilation has also transformed our understanding of memory and consciousness. Our brains process information and form memories based on electrical and chemical signals that occur at specific rates. If time dilation affects these processes, then consciousness itself becomes relative to gravitational environment. The subjective experience of thought, memory, and awareness depends on the local flow of time. This leads to fascinating speculation about how consciousness might evolve or adapt in different gravitational environments. Beings that evolved in stronger gravitational fields might process information and form thoughts at different rates compared to beings from weaker gravitational environments. Their subjective experience of consciousness could be fundamentally different, even if the underlying biological or technological mechanisms are similar. The cultural implications of gravitational time dilation become apparent when we consider how human societies might develop in different gravitational environments. Civilizations that arise on planets with stronger gravity would experience time differently than civilizations on planets with weaker gravity. Their art, music, literature, and philosophy would be shaped by their unique relationship with time. These cultural differences could become profound over long periods. A civilization that experiences time more slowly due to strong gravitational effects might develop very different values, priorities, and worldviews compared to a civilization where time flows more rapidly. The pace of social change, technological development, and cultural evolution would be fundamentally different in each environment. The economic implications are equally striking. Trade and commerce between different gravitational environments would require complex calculations to account for time dilation effects on contracts, delivery schedules, and financial agreements. Interest rates, payment terms, and business cycles would all need to be adjusted for the different rates of time flow experienced by trading partners. Legal systems would face unprecedented challenges in defining concepts like liability, statute of limitations, and criminal responsibility when parties involved experience time at different rates. How do you determine whether someone is late for an appointment when they experience time differently than you do? How do you establish fair trial procedures when witnesses and defendants have experienced events at different temporal rates? The implications for human relationships are perhaps most poignant. Families separated by different gravitational environments would gradually drift apart, not just spatially, but temporally. Parents and children living in different gravitational fields would age at different rates, creating generational differences that compound over time in ways that have no precedent in human experience. Love and friendship across gravitational boundaries would require new forms of understanding and commitment. Partners who spend time in different gravitational environments would literally share different amounts of subjective time together, even when they're physically reunited. The traditional concepts of growing old together or sharing a lifetime take on entirely new meanings when lifetime itself becomes relative. Educational systems would need to be completely reimagined for a universe where students and teachers might experience time at different rates. How do you design curricula and graduation requirements when the pace of learning depends on gravitational environment? How do you compare achievements and qualifications across different time dilation conditions? The concept of historical records becomes complex when different civilizations experience time at different rates. Events that seem recent to one group might be ancient history to another, depending on their respective gravitational environments. Establishing common chronologies and historical frameworks would require sophisticated understanding of relativistic effects. Religious and spiritual traditions would need to grapple with fundamental questions about eternity, divine timing, and the nature of existence when time itself is relative. Concepts of afterlife, reincarnation, and spiritual development would need to be reconsidered in light of the fact that time flows differently throughout the universe. the artistic implications are equally profound. Music composed in one gravitational environment would sound completely different when performed in another. Visual art that depends on timing, such as film or video, would be experienced differently by audiences in different gravitational fields. New art forms might emerge that specifically explore the aesthetic possibilities of gravitational time dilation. Scientific collaboration across different gravitational environments would require entirely new protocols for coordinating research, sharing data, and validating experimental results. The peer review process would need to account for the fact that researchers in different locations experience time at different rates, affecting their ability to replicate experiments and compare findings. The psychological health implications of understanding gravitational time dilation could be significant. Some people might experience existential anxiety when confronted with the reality that their experience of time is not universal or absolute. Others might find liberation in understanding that time is more flexible and relative than previously thought. The development of human intuition and common sense would need to evolve to accommodate relativistic thinking about time. Children growing up in a universe where gravitational time dilation is commonly understood would develop very different intuitive concepts about time, causality, and simultaneity compared to previous generations who assumed time was absolute. Sports and competitive activities would face unprecedented challenges when participants experience time at different rates due to gravitational effects. How do you establish fair rules and timing standards when the flow of time itself varies depending on location? New categories of competition might emerge based on gravitational environment rather than just skill or physical ability. The implications for literature and storytelling are fascinating. Narrative structures that depend on specific timing relationships between events would need to be reconsidered when different characters experience time at different rates. New literary techniques might emerge that explore the dramatic possibilities of gravitational time dilation. The development of artificial intelligence and computer systems would need to account for the fact that processing speeds and computational rates depend on gravitational environment. AI systems operating in different gravitational fields would literally think at different rates, raising questions about fairness, compatibility, and communication between artificial intelligences. Medical practice would face revolutionary changes when treating patients who have spent time in different gravitational environments. Aging rates, metabolic processes, and biological rhythms would all be affected by gravitational time dilation, requiring new approaches to diagnosis, treatment, and health maintenance. The concept of retirement and life planning becomes complex when career length and aging rates depend on gravitational environment. People who spend portions of their careers in stronger gravitational fields would experience different amounts of subjective time, affecting everything from pension calculations to career progression expectations. Transportation systems would need to account for the fact that travel time depends not just on distance and speed, but also on the gravitational time dilation experienced during the journey. Scheduling systems would become incredibly complex when passengers and cargo experience different amounts of subjective time during transport. The implications for insurance and risk assessment are staggering. How do you calculate life insurance premiums when lifespan depends on gravitational environment? How do you assess accident risks when the timing of events becomes relative to the observer's gravitational situation? Emergency response systems would face unprecedented challenges when emergencies occur across different gravitational environments. Coordinating rescue operations, medical response, and disaster relief would require careful consideration of how time dilation affects communication and response times. The development of social media and communication networks would need to evolve to handle the fact that users in different gravitational environments experience time at different rates. Message timestamps, notification systems, and real-time communication would all require relativistic corrections to function properly across gravitational boundaries. The implications extend to the most basic human activities. Cooking recipes would need to specify not just temperature and ingredients, but also the gravitational environment where the timing instructions apply. Exercise routines, sleep schedules, and daily rhythms would all be affected by local gravitational time dilation. Even concepts of punctuality and social etiquette would need to evolve. Being on time for social gatherings becomes a complex relativistic calculation when participants experience time at different rates. New social norms would emerge to handle the coordination challenges created by gravitational time dilation. The legal definition of concepts like reasonable time, due process, and speedy trial would require fundamental revision when courts must handle cases involving parties from different gravitational environments. Contract law would need entirely new frameworks for handling agreements that span different time dilation conditions. Urban planning and architecture would need to consider the gravitational time dilation effects of building height and underground construction. The choice of where to locate important facilities would depend not just on accessibility and cost, but also on the temporal environment created by local gravitational conditions. The implications for democratic governance are profound. How do you conduct fair elections when voters experience time at different rates? How do you establish representative government when constituents' subjective experience of political terms and policy implementation varies based on their gravitational environment? Scientific ethics would face new challenges when research involves subjects experiencing different rates of time flow. Informed consent procedures would need to account for the fact that the duration and timing of research participation depends on gravitational environment. Longitudinal studies would become incredibly complex when subjects age at different rates. The development of international standards and regulations would require unprecedented coordination across different gravitational environments. Establishing common units of measurement, safety standards, and quality control procedures becomes complex when the flow of time itself varies between locations. Personal relationships would evolve new forms of intimacy and connection adapted to relativistic circumstances. Couples might develop rituals and traditions that account for the different amounts of subjective time they experience together. Family traditions would need to adapt to the reality that different family members might age at different rates. The concept of legacy and inheritance becomes complex when beneficiaries experience time at different rates than those leaving the inheritance. Estate planning would need to account for the fact that the passage of time between the creation of a will and its execution depends on the gravitational environments of all parties involved. Educational assessment and credentialing would face challenges when students and institutions experience time at different rates. How do you compare academic achievements when the duration of study programs depends on gravitational environment? Professional licensing and certification would require new frameworks for handling relativistic timing effects. The implications ripple through every aspect of human civilization, forcing us to reconsider our most basic assumptions about time, causality, and existence itself. Gravitational time dilation isn't just a curious feature of extreme physics, it's a fundamental aspect of reality that touches every dimension of conscious experience in a universe where time itself bends to the will of gravity. As we continue to develop more sensitive instruments and explore more extreme gravitational environments, these philosophical and practical implications will only become more pronounced. We're standing at the threshold of a new era where understanding gravitational time dilation isn't just important for physicists and engineers, but for every thinking being trying to understand their place in a universe where time itself is relative, personal, and infinitely more complex than our ancestors ever imagined. The journey we've taken through the strange world of gravitational time dilation reveals something profound about our universe. From Einstein's revolutionary insights to the atomic clocks that prove time runs differently on each floor of a building, from the extreme time warping near black holes to the GPS satellites that must account for these effects every second of every day, we've seen that time itself is far more mysterious and malleable than we ever imagined. What started as an abstract mathematical prediction has become one of the most thoroughly tested and practically important phenomena in modern physics. The fact that your head experiences time slightly differently than your feet, that astronauts age more slowly in space, and that massive objects literally bend the flow of time around them forces us to abandon our intuitive understanding of temporal reality. The mathematics are elegant and precise. The experimental confirmations are overwhelming. The technological applications are essential to modern life. Yet perhaps the most remarkable aspect of gravitational time dilation is how it reveals the deep interconnectedness of space, time, matter, and energy. Einstein showed us that these aren't separate phenomena but different aspects of a unified fabric that responds to mass and energy in ways that create the temporal landscapes we experience throughout the cosmos. Every massive object in the universe, from the smallest asteroid to the most supermassive black hole, contributes to this cosmic symphony of time dilation effects. Every location in space has its own unique temporal signature determined by the gravitational influences surrounding it. The rate at which you experience time right now depends on your precise position within this invisible web of gravitational fields that permeate every corner of reality. The practical implications extend far beyond academic physics. The smartphone in your pocket can pinpoint your location because we understand how gravity affects time. The internet infrastructure that connects our global civilization requires constant corrections for gravitational time dilation. Financial markets, power grids, telecommunications networks, and scientific instruments all depend on our ability to measure and predict these temporal effects with extraordinary precision. Looking toward the future, gravitational time dilation research promises discoveries that will make today's understanding seem primitive. Quantum sensors that can detect the gravitational effects of mountains and underground rivers. Space missions that will test Einstein's predictions in the extreme environments around black holes and neutron stars. Laboratory experiments that probe the intersection between gravity and quantum mechanics in ways that could reveal entirely new physics. The philosophical implications are equally profound. Living in a universe where time itself is relative and observer-dependent challenges our most basic assumptions about existence, causality, and consciousness. The comfortable notion of a universal timeline that applies everywhere gives way to a more complex reality where each observer carries their own personal relationship with time. Yet there's something beautiful about this complexity. The universe operates according to mathematical principles so elegant and precise that we can predict exactly how much time will slow down in any gravitational field. The same equations that describe time dilation near a black hole also explain why GPS satellites need constant time corrections. The universe reveals its secrets through mathematics that connect the most extreme cosmic phenomena to the mundane technology we use every day. As we continue pushing the boundaries of measurement precision and exploring more extreme gravitational environments, we're discovering that Einstein's century-old insights continue to yield new truths about the cosmos. Each more sensitive atomic clock, each more precise experiment, each more sophisticated computer simulation reveals new layers of complexity and beauty in the relationship between gravity and time. The story of gravitational time dilation also demonstrates how scientific discoveries that initially seem purely theoretical often end up transforming human civilization in unexpected ways. What began as Einstein's thought experiment about equivalence between gravity and acceleration has become essential knowledge for anyone working with precision timing, space exploration, or fundamental physics research. Perhaps most remarkably, gravitational time dilation shows us that we're living in a universe far stranger and more wonderful than our everyday experience suggests. The steady, predictable flow of time that seems so natural and universal is actually just one small slice of a much larger temporal reality that spans scales from the quantum to the cosmic. Every second you experience, every moment of consciousness you enjoy, every heartbeat that marks your passage through life occurs within a gravitational field that shapes the very rate at which time flows around you. You're not just living in space, you're living in space-time, where the presence of matter and energy creates a rich tapestry of temporal environments that extend throughout the observable universe. The next time you check your phone's GPS location, remember that you're relying on our understanding of how gravity warps time. When you synchronize your watch or schedule a video call across time zones, consider that the precision required involves corrections for gravitational effects that Einstein first predicted over a century ago. The modern world operates on timing so precise that we must account for relativistic effects that our ancestors never imagined. The universe has been conducting this incredible experiment in gravitational time dilation for nearly 14 billion years, creating natural laboratories where we can study how gravity and time interact under every conceivable condition, from the gentle time dilation effects we experience on Earth's surface to the extreme temporal distortions near black holes where time nearly stops. The cosmos provides examples of gravitational time dilation across an enormous range of scales and conditions. We're fortunate to live in an era when our technology has become sophisticated enough to measure these effects directly, and our theoretical understanding has developed enough to predict them with mathematical precision. The convergence of experimental capability and theoretical insight has opened windows into aspects of reality that remained hidden for most of human history. As we look toward the future, gravitational time dilation will continue to surprise us with new applications and deeper insights into the fundamental nature of reality. The phenomenon that once seemed like an impossible consequence of abstract mathematics has become one of the most practical and important aspects of modern science and technology. The journey that began with Einstein's simple insight about falling elevators has evolved into a comprehensive understanding of how mass and energy shape the flow of time throughout the universe. Every measurement confirms that we live in a cosmos where time itself is dynamic, relative, and intimately connected to the distribution of matter and energy on every scale, from the quantum to the galactic. The beauty of gravitational time dilation lies not just in its mathematical elegance or technological importance, but in how it reveals the deep unity underlying apparent diversity in our universe. Space and time, matter and energy, gravity and acceleration are all different aspects of a single geometric reality that manifests itself in ways we're only beginning to fully appreciate. Understanding gravitational time dilation changes how we see ourselves and our place in the cosmos. We're not separate observers watching a universe unfold according to absolute laws. We're participants in a relativistic reality where our own experience of time depends on where we are and how we move through the gravitational landscape that surrounds us. The implications extend into every corner of human experience, from the most practical technological applications to the deepest philosophical questions about the nature of existence itself. In a universe where gravity makes time move slower, we're forced to reconsider everything we thought we knew about causality, simultaneity, and the relationship between physical reality and conscious experience. The story of gravitational time dilation ultimately reveals something profound about the nature of scientific discovery itself. The universe operates according to principles that often contradict our intuitive expectations, yet these same principles can be discovered through careful thought, precise measurement, and mathematical analysis. What seems impossible at first often turns out to be not just possible, but essential for understanding how reality actually works. Einstein's insights about gravity and time continue to guide us toward discoveries that reshape our understanding of the cosmos and our place within it. The phenomenon of gravitational time dilation stands as one of the most beautiful examples of how human curiosity and ingenuity can unlock secrets about the universe that transform both our theoretical understanding and our practical capabilities. As we continue this journey of discovery, gravitational time dilation will undoubtedly reveal new surprises and deeper truths about the nature of space-time. The universe is vast, mysterious, and more intricate than we can currently imagine. But through phenomena like gravitational time dilation, we're slowly learning to read the cosmic script written in the language of warped space-time and flowing time. The next time you check the time on your phone, pause for a moment and consider the extraordinary journey that simple digital display represents. Those numbers aren't just arbitrary markers counting off identical seconds. They're the end result of a cosmic dance between gravity and time that's been playing out since the birth of the universe itself. Your phone receives its timing signals from GPS satellites orbiting 20,000 kilometers above your head. But those satellites aren't just floating in empty space. They're swimming through a sea of curved space-time where every massive object in the solar system contributes to the gravitational symphony that determines how fast time flows. The engineers who designed your phone had to account for the fact that time literally runs differently at different altitudes, different speeds, and different positions within Earth's gravitational embrace. This isn't abstract physics anymore. This is the hidden reality underlying every moment of your existence. Right now, as you sit here, the atoms in your body are experiencing time at a rate determined by your exact position within Earth's gravitational field. Move to the top floor of a skyscraper, and those same atoms will experience time slightly faster. Descend into a basement, and time slows down by an amount so small you'd never notice, yet so real that our most precise instruments can measure it. The profound truth is that gravitational time dilation reveals something fundamental about the nature of existence itself. We don't just live in the universe, we live in space-time, where matter and energy create the very framework within which events can occur. Every star, every planet, every grain of sand contributes to the gravitational architecture that shapes how time flows throughout the cosmos. When astronomers peer into space with their most powerful telescopes, they're not just looking across vast distances, they're looking across regions where time itself flows at different rates. The light from distant galaxies has traveled through gravitational fields of varying strengths, each one leaving its signature on the radiation that eventually reaches Earth. We're literally seeing the universe through the lens of gravitational time dilation. The story doesn't end with our current understanding. We're standing at the beginning of a new chapter in physics, where gravitational time dilation might hold the keys to unlocking mysteries we haven't even learned to ask about yet. Dark matter, dark energy, the unification of quantum mechanics and general relativity, the nature of consciousness itself. All of these frontiers may be connected to how gravity shapes the flow of time in ways we're only beginning to glimpse. Future generations will look back on our era as the moment when humanity first learned to read the temporal signatures written in space-time itself. They'll see us as the generation that discovered how to use gravity's effect on time as a tool for exploring reality's deepest secrets. From mapping Earth's interior structure to detecting gravitational waves from colliding black holes, from synchronizing global communications to navigating through the solar system, we've learned to harness one of the universe's most fundamental phenomena. But perhaps the most important lesson gravitational time dilation teaches us is humility. Our everyday intuitions about time, space, and causality are just local approximations that work well enough for our limited human experience. The universe operates according to principles that transcend our common sense and challenge our most basic assumptions about reality. Einstein's greatest gift to humanity wasn't just a new theory of gravity, it was a new way of thinking about the relationship between mind and cosmos. He showed us that the universe is under no obligation to conform to our expectations. Instead, we must stretch our minds to accommodate the strange and wonderful ways that reality actually behaves. The phenomenon of gravitational time dilation continues to remind us that we're part of something far grander and more mysterious than we often realize. Every tick of every clock, every heartbeat, every thought occurs within a gravitational field that connects us to every other massive object in the observable universe. We're not isolated beings floating in empty space. We're integral participants in a cosmic web of gravitational relationships that extends across billions of light years. As we push deeper into the quantum realm and farther into the cosmic depths, gravitational time dilation will continue to guide our understanding of how the universe really works. The effects that once seemed impossibly subtle are becoming the foundation for technologies and discoveries that will reshape human civilization in ways we can barely imagine. The universe has been patiently teaching us about the relationship between gravity and time for over a century now. Each new measurement, Each more precise experiment, each theoretical breakthrough brings us closer to understanding our place in a cosmos where time itself dances to the rhythm of gravitational fields. This is the universe we actually inhabit, not the simple clockwork cosmos of Newton's imagination, but Einstein's dynamic space-time, where matter tells space how to curve and curved space tells matter how to move, where time flows like a river shaped by the gravitational landscape through which it passes. The next time you experience a moment of wonder at the night sky, remember that you're not just looking at distant lights, you're seeing evidence of gravitational time dilation at work throughout the cosmos. Every star, every galaxy, every cosmic structure you observe exists within its own unique temporal environment, experiencing time at rates determined by the gravitational fields that surround them. We are citizens of space-time, temporary arrangements of matter and energy, experiencing consciousness within a universe where gravity makes time move slower, and that truth, more than any other discovery in the history of science, reveals just how strange, beautiful, and interconnected our cosmic home really is.